Next up in our unit on electricity, we have Coulomb's law, and you're going to notice right away that Coulomb's law looks very similar to Newtonian gravity. So Coulomb's law talks about the force of two electrically charged particles on each other. K is Coulomb's constant, then we have Q1, Q2, and all of that is over R squared. So K, Coulomb's constant, is just equal to 1 over 4 pi epsilon naught. What does that mean? You don't have to worry about it, but basically it just has to do with how space-time is configured. It's just the way that charge distributes over space. But it has a value that is nearly 9 times 10 to the 9 Newton meters squared per Coulomb squared. Weird unit, but it makes the rest of this work, so we end up with force. So what does it mean, though? If we have two positive charges or we have two negative charges, what's going to happen to the sign? They're going to cancel out. So when positive, our force is repulsive. It's when you have two charges of the same sign. But when we get a negative value, force, I don't know why I put force is attractive. So if I end up with a positive and negative up there, their signs won't cancel out, so I end up with a negative sign overall. So just like with Newtonian gravity, as your radius increases, force decreases exponentially. And as R decreases, force increases exponentially. That's just because of the square value there. Let's do a practice problem with it. I'm going to erase this just so I have a little more room to work. I want you to find the net force on Q3 from the other two particles that are with it. So let's say we've got this distance up here. Let's say our distance between our first two particles, 30 centimeters, and our distance between the other two particles are 20 centimeters. We'll call this guy Q1, Q2, Q3, where Q1 has a charge of -8 microcoulombs, charge 2, +3 microcoulombs. I don't know why I put a Q, microcoulombs with a C, and -4 microcoulombs. These are just the units. Coulombs are the unit of charge. So now what I want you to do is attempt to determine the charge on Q3. Go ahead and pause the video. In just a second, we'll be back to go over it. All right, so when we take a look here, we have our force. I did force 1, 3 because it's the force between 1 and 3. And then force 2, 3 because it's going to be a combination of two forces. This charge acts on that charge. This charge acts on that charge. We're looking for what the net force is, so we're going to have to add these up in just a second. For the first one, we've got our K value and the K value for both of them. Remember that micro, this mu, Greek mu, it just means times 10 to the -6. So this is going to be 8 times 10 to the -6 coulombs, -4 times 10 to the -6 coulombs. Both of these are negative. The only one that's positive is our 3 one down here. Now you would expect bigger charge, bigger force, but if you look at the distance, this one's significantly larger than that one. So what we find is even though this charge is smaller in absolute value, it is closer, and we end up with a bigger force from it. Now, what does the fact that this one's positive and this one's negative mean? The fact that this one's positive means it's repulsive. So if we look at where Q1 and Q2 or 3 are, they're going to be pushing away from each other. So on Q3, this should be a force to the right. Make my arrow look a little better there. Over on Q2, it's going to be an attractive force, meaning it's pulling them together. So on Q3, it should be pushing it to the left. So I have 2.7 newtons to the left, 1.15 newtons to the right, which means overall I'm going to be left with 1.55 newtons left. And that's my solution for that problem. All right, I've got another problem up here, and this is where things start getting a little harder. It's no longer a one-dimensional problem. We now have a two-dimensional problem. So I want you to find the net force on Q2. I'll walk you guys through how to do it for Q2, and then I want you to try it out for your own for Q3. So when I see this here, I want to find on Q2 what is the net force. I know these two are both positive, so this one should be pushing it down. This one's negative, this one's positive, so it should be attracted to the right. So I'm going to need two different things in this problem. One, an absolute magnitude, so how strong is the force, and then two, what direction is it going in. So to first find out the forces, I need to know what forces are on it. There's going to be a force between 1 and 2. There's going to be a force between 2 and 3. So let's solve for those. It's kq over r squared, kq over r squared. So this is Coulomb's constant, newtons, square meters per Coulomb squared. Then we have a 65 microcoulomb charge on the top, attracting or repelling a 50 microcoulomb charge on the bottom. I'm going to divide that all by the distance between them, 0.3 meters. Ooh, that's a weird M there. We'll solve that one. Then over here, same idea. We're going to use Coulomb's constant there. Again, we're going to have our 50 microcoulomb charge. That's charge 2. It's still going to be there. But now we have our negative 86 microcoulomb charge attracting it. And then we are dividing that all by the distance between them, which is half a meter. Half a meter here. When I plug those numbers in, I get a force of 325 newtons. Since that's repulsive, that's going to be downward. Then over here, I get a force of 155 newtons, which means that's going to be to the left. Because, oh, sorry, for Q2, not Q3. Q2 is going to be pulled to the right because it's attracted to this one, so this will be rightward. Now that we have two different force vectors, we're going to have to do some algebra and do some trigonometry to figure out where it's going. So in this one, we've got 155 newtons this way, and we have 325 newtons downward. So our resultant force should look something like this. First thing I want to know, what angle does it make relative to the horizontal? So when I do that, I'm going to have to do opposite over adjacent, that's tangent. So tangent of an angle is equal to the opposite, which is 325 over 155. So if we take the arctan of 325 over 155, we find that we get an angle of 64.5 degrees. So that's going to be 64.5 degrees south of east. Next thing we need to do is find out our resultant force. And to do that, let me take a second here. Boop, 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 boop. Is I need to do the Pythagorean theorem. So a squared plus b squared equals c squared. Square root of 155 squared plus 325 squared equals 360 newtons. Now what I want you to do with this is combine it together. Final answer, angle and a force magnitude. So I would say 360 newtons at 64.5 degrees south of east. You could also find this angle here. Let's call this 1 and 2. If you were to find the second angle, you would say east of south. Same idea. It's just going to be 90 minus that value is what that angle is. So as long as we can communicate the same thing, we're cool. Now what I want you guys to do is find the net force on charge 3 over here. And on this one, I'm going to warn you, you're going to have to break your vectors apart into their x and y components and then solve for it from there. So go ahead. I'm going to pause the video. You should do the same. When we come back, we'll go over how to do it. All right, this probably looks like the board of a conspiracy theorist right now, but trust me, we're going to get through it. We're going to understand it. So for Q3 is what we're trying to find the net force on. If we look over here, I've drawn a line. it's real easy to find force 2, 3 because it's just the opposite of what it was before. Before we were looking at 2, it was attracted to the right by Q3. Now we're looking at Q3, so it's going to be attracted to the left by Q2. But now we have an angle between Q1 and Q2. So to find it, we're going to need to find the new distance between them, and we're going to have to find the angle. So we plug in our Coulomb's constant. We got our charges here, but now we need to know the distance. It's not listed up here, but it's a triangle, so that makes it easy. We just do Pythagorean theorem, find out the distance between them. So now I get a distance of 0.58 meters. When we plug in the value, we get about 201 newtons, but now we need to know an angle too, because we need to know how it's situated in space. So we come over here, and we do the inverse tangent because our angle's there, so opposite over adjacent, 0.3 over 0.5 gives us a 31 degree angle. So that's 31 degrees north of west. That's what we get here, 201 degrees north of west. Next thing we need to do is break this thing into its components, because to be able to solve it at the end, we need to know how much up it goes, how much over it goes. Because we're using an XY plane here, why don't I say positive is this way for X, negative is that way for X, positive is this way for Y, negative is that way for Y. So we need to break this one into its components. F23 is easy because it's only to the left. That would be a negative 155 newtons, since we're defining left as negative. Over here, we have our angle, 31. We have Y and X, and here is our net force from 1, 3, or our force of 1, 3. So 201, if I solve for my Y, I use sine, I get an upward force of 104 newtons, so that's positive in the Y direction. Then over here for cosine, it's to the left, and I get 172 newtons in the left direction. I'll make that negative. So I come over here to this chart. Here's my force 1, 3. Here's my force 2, 3. And then I'm just going to add them up and solve for the net forces here. I just take the values I got there and that value, plug them in. Notice F23 not going up or down, so it has no Y value. I'm going to add these values up. And here's the X and Y components of my net force. Now that I've got that, I'm going to make a triangle for it. With this triangle over here, it shows I'm going upwards and to the left from the origin. Now I can solve for my total value. I just use Pythagorean theorem again. A squared plus B squared equals C squared. I get 386 newtons as the magnitude of my force. Then I use the inverse tangent again, opposite over adjacent, and I find that the angle is 15.6 degrees. That makes sense. It was a bigger angle. We add a little more to the left, and now it's a more shallow angle. So I end up with 15.6 degrees. That's still above the leftward, the negative horizontal axis. So I have 15.6 degrees north of west. And that is going to do it for our notes on Coulomb's law.